Anybody here? How many? Oh, well. Okay, guys, can you hear me who are attending virtually? People attending virtually, can you hear me? Can you please like comment in the chat, guys? You okay? I guess nobody's there. Well,
Everybody's busy for midterm.
why is there midterm? Are there midterms?
It's 206. 2 days from
Oh, okay. So math 206?
now.
Oh, 206. Okay. Okay, so yes, so they can hear me. So okay. You can see the board clearly, I guess. Okay, so let's talk about group actions.
It's also people outside.
What do you mean?
I think there's still people outside. I don't know.
People outside. Okay, so let's just talk about group actions. Let's give some examples of group actions. I mean, let's prove. Let's use some exercises to group actions. Let's use some group actions to do some exercises. Okay, so remember what a group action is? Should I define it again? Of course, we know that. We know that? Okay, great. So let's first prove a nice theorem. Let G be a group and let HK be subgroups of G finite index. Okay. So G, H, G, K are finite. I mean, G is not necessarily finite, but the index of H and the index of K are finite. Prove that pretty cool formula, pretty cool result. That the index of the intersection is finite, and it's bounded above by the product of the two indices. Now, what would be a good idea here? How would you use group action to prove that? So, like, a good idea here is to express H to find an action and a point whose stabilizer is H intersection K. If I manage to express H intersection K as a stabilizer, I get that G, the index of the stabilizer in G, is less or equal than that. Right? Now, if I manage to have the set here of this size, then that would be obvious. Then the size of the orbit is less or equal than the size of the set if my set is of this size. Now, we know that G mod H has size index of H, right? And G mod K has size index of K. So how can I find a set whose size is the product of these two? To be honest, this has nothing to do with group actions. I have a set of size 3 and a set of size 2. How do you construct a set of size 6? By using these two sets. This has nothing to do with group actions, it's a set of pairs. The set of pairs, right? Yeah. So it's G mod H. It's G mod K, right? What is the size of this set?
The extension.
Yeah, agree. We agree or not? Is that clear? G mod H and G mod K has size. right?
I mean, G is another group.
G is not finite.
G
This
is
is
another group.
G is it?
G is a finite group.
G is a group.
Also finite group.
Not necessarily.
You look at Z2, then look at the first point and the second one. They have index 2, but the intersection is just identical. Infinite on the left side. Finite on the
Where are you saying? Oh, you mean G here is a finite? Yeah. Okay. Oh, yeah. Sure. Yeah. Yeah. Thanks. 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 So where okay. Let's assume it's finite, but G mod H, G mod K. We agree with this, that this has size this? Is it clear? Yeah. Okay. Now, can you define an action of G? G mod K times G mod H times G mod K? How do you let this act? How would you define this? If you define this way, do we get a group action or not? Yes or no? Did you try? Yeah, we get a group action, no? Yeah. Finds an action G on G mod H and G mod K. We agree with this or not? This defines an action, no? You guys see this? Okay. Now I'll take an element. What's the stabilizer of HK? Of the pair HK? This is G and G such that V star HK is equal to HK. This is just G and G such that GH is equal to H and GK is equal to K. It's just H intersection K. Agree or not? Yeah. We agree? What can I say about the index of the stabilizer? What can I say by the orbit stabilizer here? The orbit of HK, well, by orbit stabilizer. Well, there is. Orbit stabilizer. G star HK has size equal to the orbit HK. I just want to make sure that one time I have the rule. The first one? So good. Yeah. Now the orbit of HK is a subset of G mod H times G mod K. This is less. No, I don't think we've used the finite assumption, but let's double check. But orbit HK is a subset of S, is a subset of G mod K, and it's G mod H. So the orbit HK agree? Everybody? Now, what is the size of the orbit of HK? This is just the size of the stabilizer of H and K. This is just the index of the stabilizer of H and K. So this is just G, H intersection K. Now, I don't think we need the assumption that it's finite. Did we need that?
Yeah, you assume infinite is equal.
Yeah, I think so. No, but all I care about is that H and K have finite index. Yeah, I think we can remove the assumption. Yeah, I think so. Because we didn't use it. Now, a good exercise would be show that if the indices are relatively prime, then G, then equality holds. So if the two indices are relatively prime, then the intersection has index the product. Do you want to see why? Okay, I mean, there's a fact that you have to convince yourself of. Okay, I will not prove it, but there is a fact to prove it only for finite groups, but it also holds for infinite groups. Thinking class to prove it for finite groups. For infinite groups, you can do a proof of that. It's not a bad idea. It's not a bad proof. That's a bit technical. So let's assume G is finite. Let's assume that G is finite just to be to do things a bit easily. So assume G is finite and GH and GK are coprime, relatively prime. Okay. What can I say about the index of you agree with this? This is because H intersection K is a subgroup of H. Everybody, we agree? And then it's also equal to GK, K intersection, H intersection K. I mean, this is true for infinite, but we did not prove it for infinite. Okay, we did not prove this for infinite. We agree? Now, what does this mean? This implies that GH, which is obvious basically, divides right? This also implies that dk divides essentially. If both of them divided, this means that the LCM right? Now, if both of these are co-primed, what is the LCM?
This the multiplication.
Is their multiplication. If GCD then LCM GH GK is equal to the product. Agree so far? Then what can I say about this? I mean, we're working with positive numbers. So this means that G mod H, the index of H, sorry, the index of K is less or equal than the index of H intersection K. We agree? Are we following or not? I'm saying that a number divides the other positive numbers. So the second one must be less, must be this one, must be bigger than the here. Now look at the first result we proved. We could bound this above by the same thing. Quotient. Then you get that G H intersection K is equal to the product of the two indices if the indices are co-prime. Interesting. If you have a group of index 2 and a group of index 3, then the index of the intersection is 6. Not an obvious fact. Not an obvious fact. Now, suppose that the okay, well let's see that. Okay, is it clear? And if the okay, so if the indices are relatively prime, the size of the orbit of HK, what is it? It's just the product of the two indices, right? This is just the size of the orbit of HK, right? This is just the size of. Like before, what can I say about the size of the orbit of HK if the two indices are relatively prime? It's equal to the full set. So this action is transitive if the indices are relatively prime. Very nice. Isn't that right? Yeah. Fine. Sorry. Yeah. Okay. Okay, great. Okay, are we good? Did we copy this down? Is it clear? Any questions on this? You can choose how stab HK gives us H cap K. Okay, so what is the stabilizer of HK? This is the set of G and G such that GH is equal to H and GK is equal to K. Agree? You agree? Yes, we agree or not? We agree? Oh, okay, great. Okay, so it must belong to H and it must belong to K. Okay, is that question clear? It's a very nice exercise. Orbit stabilizer, which is pretty nice. Okay. Let's do one more on homomorphisms. Okay, let's see if I can come up with something nice. Let G be a simple group. We all know what a simple group is. What's a simple group? The only ones. Remember this? So let G be a simple group. G be a assume that G is a subgroup H of index n. And a stricted group that you just again finite. So that side of G divides n factor. That's a subgroup. Let me check if that's true. How do you do that? Yes.
You can try to find the homomorphism between G and the Sn,
Exactly.
and then you have to show that it's injective.
Very good. Now you're looking at the n factor and looking at the order of G. So and you show it's injective. Great. Very good. Very good first step. Now where does the n come from? What is this homomorphism? What do we call this homomorphism? What did we call it in class? The set representation. Yes or no? Remember that? So, I mean, let's recount this. Let's rewrite this. So we know. Do you want me to go through all of this again, or just give you the answer to this? I can just give the answer. So let n be the kernel of the coset representation. G is simple, and n is contained in H, so n must be 1. So G must inject into the symmetric group of G mod H, which is Sn. Yeah, sure. Sure, very good. G acts on G mod B. We have G mod H, sorry. We agree with this? Yeah. And this action induces a homomorphism rho from G to the symmetric group of G mod H, which is isomorphic to Sn. So really you have a homomorphism from G to Sn. Agree or not? Everybody. 100%. We agree or not? By the class theorem, I have a group action on G mod H, and then I have a homomorphism from G to the symmetric group of G mod H. Class theorem, right? Remember that? Open your notes. Yeah. Great. Now the kernel of rho is contained in H. Remember that? We showed that the kernel of rho is equal to the intersection which is contained in H. Agree? Now, can the kernel of rho be equal to G if H has index bigger than 1? H is not the entire G, right? H is different than G. So H is a subgroup of G, and H is different than G, hence her rho is different than G. Now, what do I know about the kernel of rho? It's a subgroup, but what type of subgroup is it? Normal. Her rho is a normal subgroup of G. So kerr rho and G is simple. So what are the possibilities for kerr rho? What are the possibilities for kerr rho?
E.g. or G.
It's identity or G. What did I prove here? That kerr rho is different than G. So what must it be? Everybody, are we good? Kerr rho. Kerr rho. Or I mean, this is obvious that kerr rho can be equal to G, even if G is not simple, right? Like, it's always true, right? Like, because H has index. This is always true. This doesn't depend on the fact that G is simple. Right? So kerr rho is G or kerr rho is equal to EG, but rho is different than G. So kerr rho is EG. Agree or not? What can I say about my homomorphism rho? Rho is injective. Hence, what is, yeah, G is isomorphic to rho of G, right? By the first isomorphism theorem. G modulo 1 modulo the kernel is isomorphic to rho of G, right? And hence, G, which is the size of rho G, divides Sn, which is n factorial. Is it clear? If it's not clear, please ask. Don't hesitate to ask. Yeah.
Can you just explain the last, like when you say G is isomorphic to the
Rho G?
yeah,
Yeah.
is it by the when you
First isomorphism theorem.
yeah.
So G modulo the kernel of rho is isomorphic to rho of G, right?
Is it and that since the kernel is identity.
So G modulo the identity is isomorphic. Very good. Are we good here? Any questions on that? Basically, this tells you that if you have a simple group like A5, you know that you cannot have a subgroup of index 3. Right? For example, if A5 has a subgroup of index 3, we know that A5 is simple. Then A5, the cardinality of A5 would have to divide 3 factorial. 60 would have to divide 6. Impossible. A5 cannot have a subgroup of index 4 because A5 would have size dividing 4 factorial. Impossible. Right? You see that? Everybody, do you see that? Okay. Tough stuff, but are we good here? Any questions? Yes.
Is this just a theorem or is it like just something?
No, this is just an exercise.
Okay.
Yeah, you can turn it into a theorem if you want. Okay, but you can turn it into a proposition here. Right. It's just an exercise. So simple groups, and then now, I mean, let's think a bit about it. Now, if n is prime, suppose that n is prime, and G is a simple group with a subgroup of index P, where P is, so suppose P prime and G is a simple group with a subgroup of index P. Can G have a higher prime factor than P, or P is the highest prime factor? Then G would have to divide P factorial, right? So P will be the highest prime factor of G. And then P squared wouldn't divide G. See that? So yeah, I mean, these are just nice number theoretical facts by playing with factorials and playing with this. Okay. So now I'm thinking of proving Fermat's little theorem with group actions. If you're interested to see that, you can prove Fermat's little theorem with group actions. Okay. Any questions on this? Like, yeah, I mean, on the homework you have to do some exercises that are a bit non-trivial, but all of them kind of use this idea. The idea of closed representation. Okay. You guys don't have questions? It's all good. I know it's not, but okay. Yeah, sure. We good? Okay. Okay. Proof of Fermat's theorem using group actions. Very nice. Very nice proof. So consider the set S of functions from Z mod BZ to 1 of 2. So I mean here I should say let n be this. Okay. Define following operation. Z mod BZ cross S to S, where I take an element of Z mod BZ and a function f gives me J star f, where J star f of x is just f of x plus. Okay, basically what an element in Z mod BZ does to the function is just it shifts it. Shifts. So f is a function from Z mod BZ to S to 1 to n. So x, it makes sense. X is in Z mod B, G is in Z mod B. I can add the whole f of this. Okay. Now this defines a group action. star is a group action. Let's prove this. What is the identity element of Z mod PZ, everyone? What's the identity element of Z mod PZ? 0, right? 0 P star F of X, just F of X, right? For any X in Z mod PZ, for all X. So 0 P star F is equal to. Now, what is J1 star J2 star F of X? That's just J1 star. What is this? This is J1 star.
X plus S.
F X plus J2, right? You agree? So this is just F of X plus J1 plus J2. This is just J1, J2 star F X. You agree, everyone? Is that clear? So this defines a group. Of course, J1, J2 are in. Let me put this here. It's actually. Okay. Just need to double check that. What did it say? It's 44. Still much. Yeah. Okay. Now, S is a disjoint union of orbits. And let's use some. We don't have to. Let's compute the set of fixed ones. What is the set of fixed ones of this action? Suppose add the fixed ones. What can I say about that? Oops, who's turn? Yeah. Yep, this one, what it says. Yeah. Suppose F is a fixed point of this action. What could I say about F? Then F. Then J star F is equal to F for all J. J1 PZ, right? Which means that F of X plus J, which implies that F of X plus J is equal to F of X for all J in Z mod PZ, for all X and for all J in Z mod PZ. Or you know what? Let's do it in a better way. That's if these two functions are equal, this means that j star f zero for all j z what pz. This means that what is j star f at 0? This is just f of j is equal to f of 0 for all j is z what pz. What can I say about f? If f is a fixed point of this action, then f is a constant function, right? Because f of 1 would be equal to f of 2 would be equal to f of 0 would be equal to so on. F some function. Conversely, if f is constant, it's clear that it's fixed, right? If f is a constant function, then j star f is equal to f for all j and z mod is. Is that clear or not? Is the last point clear? So pick f to be a constant function. So I mean, let me write this better way. If f is constant, if f is constant, f is constant. This means that f of 0 is equal to f of 1 is equal to f of p minus 1. Equivalence class. Equivalence class. Okay, this is what it means. So what is j star f of x? It's just f of x plus j. Now, if f is constant, then f of x plus j is equal to f of x. Okay, so j star f. Agree or not? So the set of fixed points is the set of constant functions. Now, Z mod PZ is a P group. Well, obviously, I mean, that's the nicest P group you can find. Let's use that theorem in class. From class in the P group. Then I know that the size of the set S is congruent to the number of fixed points mod P. Remember this from class? For P groups? I mean, I didn't have to use it, but let's use it. Remember this from class or not? Yesterday we did this. You remember that? Now, what is the size of S? How many functions can you find from Z mod B to 0, 1 to N? To 1 from 1 to N? N, right? And no, how many functions can you find from S to N? From Z mod B, Z to N, sorry. From here? So how many choices do you have for the equivalence class of 0? N choices. Equivalence class of 1, N choices. Equivalence class of 2, N choices. So the cardinality of S is N to the P. Right? Now, how many constant functions do you have? How many constant functions do you have from Z mod PZ to 1 to N? N, right? So NP is congruent to N 1. Okay, very multiple theorems. course, if P doesn't divide N, we can cancel it and get N to the P minus 1 is congruent. Right? Very nice. Power of group actions. They're very powerful. Any more questions? Okay, so let's end this.